Hello everyone, my name is Diego Infante-García and I'm here to present the work with the title Crack Orientation Criteria for Non-Proportional Loading based on Stress Intensity Factors and Near Crack Tip Stress Fields. So this work has been done in collaboration with Professor Henar Miguélez from the same department as I am, the Department of Mechanical Engineering at University Carlos III of Madrid, and Professor Henar from Technical University of Valencia. So this slide shows the contents of my presentation. I will start with a short introduction of the topic, and then I will review some of the crack orientation criteria and explain the methodology. Next, I will present the crack problems that we analyze, and finally, I will show the predictions of the crack trajectories. I will finish with the main conclusions of this work. So let's start with the introduction. It is well known that crack paths are usually kinked or slightly curved. Under the assumptions of linear elastic fracture mechanics, this is usually caused when loading under non-uniform stress field, as those found in almost any real application. Although cracks are usually three-dimensional, we will reduce this work to study two-dimensional planar cracks, which is the most studied case in literature. We can see in the right figure a clear example of how a planar crack growing in a pure mode 1 gains a different orientation angle when these cracks are loaded under a mixed mode. And it is observed that those cracks tend to grow in a direction close to where K1 is maximum or where K2 is minimum, following the criterion of local symmetry. When we have proportional loading conditions, which means that the principal stress directions remain constant during loading, the conventional criteria such MTS, the maximum tangential stress direction, or the maximum energy release rate lead to similar and also satisfactory results. However, under non-proportional loading, when we have the variation of the principal stress directions and thus the stress loading radius change, the results, the predictions are not always as satisfactory as in proportional conditions, and we can find significant difference between the criteria in the literature. In the literature, we can find different fatigue tests that are used to study the effect of multi-axiality and non-proportionality. So the most common tests found can be tabular specimens under axial torsion loading, biaxial testing machines, or fretting fatigue tests. In this work, we are going to focus on the last two tests since we are going to work in two-dimensional conditions. And the goal of this work is to review different crack orientation criteria for non-proportional loading in a cruciform specimen and in a fretting fatigue problem. So let's start talking about the crack orientation criteria for non-proportional loading. In a crack propagation model, before to apply a crack orientation criteria, first we need to model these cracks. And in this work, we have used the standard finite element method, which has the advantage that we only require a single mesh that is independent of the crack, and so we don't need for remeshing techniques as in conventional finite element method. So in this case, the discontinuity is introduced by enriched degrees of freedom, and this is very useful for crack growth analysis and for parametric analysis. We have used an in-house implementation that introduces crack face contact and also a post-processing subroutine to calculate the stress intensity factors via interaction integral. The methodology that we use is the classical approach where we start with an initial crack with a certain length and certain orientation. It's a segment crack. We perform a simulation, then we analyze either the stress field or we perform the stress intensity factor analysis to obtain the SIFs. And then we apply a crack orientation criteria. At the end of each simulation, we extend the crack and we repeat the process. Since the focus of this work is the crack path, we repeat the process until obtaining a predefined crack length. When we want to assess the crack path, we need to know at which angle the crack will kink, and to this end, we will require for a crack orientation criteria. In this work, we're going to review two main groups of crack orientation criteria. On one hand, those based on the stress intensity factors analysis. So these criteria need for the stress intensity factor calculation, obviously, and also to use some relationships that establish the stress intensity factors of a crack emanating from the original crack, that naming as K lowercase with asterisk with the original crack. We will talk later on this relationship, and well, in this group of criteria we can find the maximum range of K1, the maximum K1, and then we have the criterion of minimum range of K2, which is in line with the criterion of local symmetry for proportional conditions. On the other hand, we have criteria based on near crack tip stress field analysis. So this criteria has the advantage that do not require to obtain the stress intensity factors, although its implementation is also not straightforward due to the singularity produced by the crack tip. However, in general, this criteria is usually more affordable from a computational point of view, as in the previous group we have different criteria based, for example, in the hoop stress or on the K1, and also minimizing the tangential stress, which is in line with the K2. As I said before, those criteria based on the stress intensity factors requires for a relationship to establish the stress intensity factors of a virtual infinitesimal crack maintaining from the original crack. These virtual stress intensity factors will also change as the stress intensity factor changes during the cycle. So here we can see that the equations that govern these virtual stress intensity factors obtained by Nuismer are basically the same as the ones that govern the stress field dominated by the first singular term. So we can guess that the results obtained by both criteria that are based on the same idea will be at least similar. So, as I said before, when we want to apply a criteria based on near-crack tip stress field analysis, and in particular numerical methods such as XFEM, we know that we obtain a discrete stress field solution. This means that during the crack propagation simulation, the points are usually located randomly at a certain distance to the crack tip. Thus, we can compare directly the stress at different angles because of the high domination of the stress singularity. So we developed a simple methodology whose main idea is to average the stress field solution of the integration point located in a circle with a radius approximately the element length, and rotate this stress field to obtain the solution at different angles. So we validate this methodology using the Westergaard problem, which has an analytical solution, and thus we compare the results obtained with the two stress field solutions. And we obtain for quite a good correlation for kinked angles around below 40 degrees. So let's start with the crack problems that we have analyzed. The crack problems, the first one is a cruciform specimen with a center per crack under biaxial loading. So in this slide we can see the dimensions of the specimen and the initial crack with a 36 millimeters at the center of the specimen at 45 degrees. And then we apply a sinusoidal displacement at both arms at different phase angles. Here we can see the three cases that we have studied, the three phase angles that we have studied. The first one is in phase loading, which means that both of the arms are loaded at the same time. We can see on the first figure that how is the loading path. Then the second case is a quadrature phase with 90 degrees. Here we can observe how is the loading phase, the loading paths, and also in the last figure we have studied the opposite phase with a phase angle of 180 degrees. And well, these are the three cases that we have studied in this specimen. The other problem that we have analyzed in this work is a fretting fatigue problem with a complete contact configuration. So as it can be seen in the left figure, this consists in a dog bone specimen axially loaded with a fatigue load, usually called bulk load, and with two indenters are clamped under constant normal load and symmetrically applied on both sides. So the specimen and the indenters are made by an aluminum alloy, and the principal dimensions are given in the sketch. In this case, the numerical model is simplified to a quarter model due to symmetry conditions. I'm going to start showing the results obtained for the cruciform specimen, and I'm going to start with the in-phase loading with a phase angle of 0. So in this figure we can observe that in the most simple case we obtain K2 0 and K1 changing, which means it's a pure mode 1, it's a proportional loading, and in this case when we apply criteria based on K1 and in K2, we can see that the maximum of K1 is the same as the maximum of the range of K1, and also the minimum of range of K2 is the same, which is 0 degrees. The prediction, the crack prediction, is a straight crack. In the case of a phase angle of 180 degrees with the opposite phase, for the initial crack inclined at 45 degrees, we can find a uniform K1 and a varying K2. This means that the crack remains open with a constant K1, while a sinusoidal K2 with a ratio of -1 is applied. This loading scenario produces two maximum of virtual K1, that is the same that the range of K1, and two minimum of K2, but at a different angle orientation. The first one at 50 degrees and the second one at a larger angle. Here, in the right figure, we can observe the predicted crack path, which is mainly a crack bifurcation due to these two local maximum. In case of a phase angle of 90 degrees, we obtain the most complex scenario in terms of loading. The resulting K1 and K2 change during a cycle. However, we can find some similarities with the previous case of 180 degrees, since the crack remains open during the whole cycle, although in this case changing. In addition, the results in terms of the virtual stress intensity factors are similar. We can find two maximum of range of K1 and two minimum of range of K2 at different angles. However, we can observe that relative maximums of virtual K1 are almost constant and cover a wide range of angles. If we compare the predicted crack paths between different criteria, we can find more or less similar crack trajectories, since all of them predict a crack bifurcation. These similarities are higher between the minimum shear stress range criterion and the minimum range of K2. Also between the maximum range of K1 and maximum K1, especially at the beginning of the crack propagation. We have found some results in the literature, as the one shown within the right figure, that proves that the better agreement is found with the criteria based on minimum range of K2. So last but not least, the fretting fatigue problem results. So following the presentation of the previous slides, we can see in this first figure the loading path that the initial crack is subjected. In this case, we can observe that it's mainly a almost constant K2 while a cyclic K1, and we also can see that the crack remains closed during a significant part of the loading time due to the contact loads. So when we apply the criteria based on virtual stress intensity factors, we can find that the maximum K1 is pointing outside the contact zone at an angle of around 40 degrees. However, if we look at the range of K1, we can see that due to this constant K2, the maximum moves towards 0. And in the case of the minimum range of K2, we can see that the minimum is located at -10 degrees and it's almost constant in orientation between 0 and -10 degrees. The predicted crack trajectories are shown in the right figure, and well, we can see that the maximum K1 is not able to predict the crack path orientation. However, the rest of the criteria has been able to predict the crack path. Two main conclusions of this work we can obtain. So crack path prediction under non-proportional loading is possible with the criterion of maximum range of K1, minimum range of K2, or the minimum shear stress range criterion, although some difference can be found between these criteria. And well, the best agreement with the experimental crack path was found when using the criteria based on the extension of local symmetry to non-proportional loading, although we will require for further investigation of this topic. So thank you very much for your attention. Here you can find my emails, so don't hesitate if you have any doubt. And well, that's all. Thank you.